In today's video, we'll look at indeterminate forms and L'Hopital's rule. That's how that is pronounced, L'Hopital's rule. What an indeterminate form is, if we break down the word, it is a form that cannot be determined. Okay, so it might be ambiguous in some way. We'll find that we can use what we'll eventually call L'Hopital's rule to evaluate these indeterminate forms. So first we'll look at a limit, something that we've worked with before. We saw back in, I believe it was Unit 2, if we had a limit like this, when we try to do direct substitution, we'll get 1 minus 1 on top, we'll get 1 minus 1 on the bottom, so the denominator is 0. Whenever the denominator was 0, we had to try and do something so that we could still evaluate it. In this case, we would factor. Top factors into x and x minus 1, bottom x plus 1 and x minus 1. And then we would look to see what cancels. The x minus 1 would cancel out, leaving us with x over x plus 1. Now this is something we could do direct substitution with, and it will give us 1/2. Well, here's another example of one. When we plug in 1, we get a 0 in the denominator. This one we don't know how to work with, though, and that's after today we will be able to work with something like this. Notice in this example we did have 0 in the bottom, which is why we had to try and simplify it some, but we also happen to get a 0 in the numerator. In this example we know we had a 0 in the denominator. Well, any log of 1 in our numerator there is also 0, so we would actually get 0 both numerator and denominator. When we get 0 over 0, that's our first indeterminate form we will look at. So if you have some limit where it's a function over another function, and both functions individually go to 0, this is called an indeterminate form, 0 over 0. Now we said indeterminate is something that we cannot determine, and here's why. We don't know which one is going towards 0 more quickly. If the numerator is going to 0 more quickly, basically we're getting really close to 0 on top, not quite as close on bottom, so the bottom's getting smaller more quickly, meaning the numerator is getting smaller more quickly, meaning the whole fraction is going towards 0. But if g of x, the bottom, is getting smaller more quickly, and the top is not getting small as quickly, when you get really, really small numbers on the bottom, that really makes your value blow up. So that would eventually go towards infinity. And hypothetically, they could potentially be going at the same speed. Well, if they're going at the same speed, then that would go towards 1. So we have several different occurrences that we could have here. So we saw this before. And what we're going to do, we already knew this was 1/2. We're going to come back to this one in a second after we learn our rule, and we'll see that we will get 1/2 once again. Now here's actually another indeterminate form that we've already seen this year. Sine of 0, 0, and when we put in 0 for x, that's 0. Now we already actually proved that this is going to be 1, but we'll show with our indeterminate forms in a second why we can get it this way now. And then we've got the situation where maybe we're approaching infinity. So that means you're really looking at a horizontal asymptote. Well, on top, natural log of infinity, that's going to get huge, so that's going to go towards infinity. And infinity minus 1 will still be a huge number. This is another indeterminate form, and here's why. We don't know which one is getting larger quicker, the numerator or the denominator. If the numerator is getting larger much more quickly, then this will go towards infinity, so that will control the value of the fraction. However, if the denominator is getting larger more quickly, that means our fraction's value will get really, really small, and we will go towards 0. So we do not know, just based off this, what it will end up being. Here's another example of that. infinity in the numerator. When you put it in for x, it'll go towards infinity. Same with the denominator. So this is another case. We don't know which one is going to something more quickly. So therefore, infinity over infinity is another indeterminate form. So we talked about this one, where if you have 0 and 0, where again f of x and g of x, those are the parts in the numerator and denominator of your fraction. Well, now we can do infinities as well. And it actually doesn't matter if it's positive infinity or negative infinity. So the indeterminate forms we have so far, we talked about the 0 over 0. You could have positive infinity over positive infinity. They could each be negatives. Or you could have one of each. You could have a minus infinity over a positive infinity, or a positive infinity over a negative infinity. All 5 of these, if we end up getting them in a limit, just by having that, we cannot determine what our limit will be. We have to be able to do something else, because we don't know which the numerator or the denominator is getting to its thing more quickly. So here's L'Hopital's rule. What L'Hopital's rule says, if you have a fraction with some function, f of x over g of x, and it is an indeterminate form, if you notice you have an indeterminate form, then use L'Hopital's rule. So if you notice, when you do direct substitution, you have either a 0 over 0, or one of the infinities over one of the infinities. That is what will tell you that you're going to do L'Hopital's rule. And here's what it says. If you have an indeterminate form, you will individually take the derivative of the numerator and the derivative of the denominator. Because that limit should be equal to the original, you'll now just reevaluate with direct substitution. And most times you'll be able to get the value of your limit. If by chance you get another indeterminate form, you just now do the derivative again. Derivative of the numerator on its own, denominator on its own. Now it's key to point out, you're not doing quotient rule. The L'Hopital's rule says take the derivative of f, the numerator part, all on its own. And on the bottom, put the derivative of g, the denominator's part, all on its own. And that's just what we talked about a second ago. Now, this could be true also if your limit is just, say, a one-sided limit. If you're just approaching something from the left or the right, not the whole entire value, L'Hopital's rule will work as well. So let's go back first, actually, to the two that we already knew, and we'll verify those. We knew earlier that this should end up equaling 1/2 eventually. We saw that with factoring and canceling out. Well, when we plug in 1, we get 0. When we plug in 1 in the denominator, we get 0. I will want to see that on a quiz or a test. I need to see that you have verified that you, in fact, have an indeterminate form. Because if you don't get an indeterminate form, L'Hopital's rule does not apply, and you shouldn't be taking the derivative of the top and the bottom. Because we get an indeterminate form, we'll now take the derivative of the top and the derivative of the bottom and reevaluate that limit. So our numerator will be 2x minus 1, and our denominator will be 2x. And now we'll reevaluate. When we put in 1, we'll get 2 minus 1, which is 1. When we put in 1 in the denominator, we'll get 2. Notice that's the 1/2 we got in the other version. The other example that we already knew was 1 from earlier in the year. We already showed this is an indeterminate form. So we'll go ahead and take the derivative, and we'll reevaluate the limit as x approaches 0. Well, the derivative of sine is cos, so we'll have cos x on top. Derivative of x is just 1. Now when we plug in 0, cos of 0 is just 1 over 1, so this equals 1. So that checks out as well. So this kind of just verifies for you that it does in fact work on a few that we've tried, but only in cases where you have indeterminate forms. So let's look at that one that we couldn't solve before. Natural log of x over x minus 1. when you plug in a 1, log of anything, or log of 1, no matter what type of log it is 0, and 1 minus 1 is 0. So this is an indeterminate form case. We'll take the derivative of the top and the bottom, each on their own. Derivative of natural log x is 1 over x. Derivative of x minus 1 is just 1. Well, anything over 1 is just itself, so really we're doing the limit of x approaches 1 of 1 over x. And now see how I just neatened it up a little bit there? That's sometimes going to be helpful just to simplify the algebra before plugging back in. It can make your life a little bit easier. Now when we plug in 1, we'll get 1 over 1, which is just 1. So in reality, our overall limit as x approaches 1 of the natural log of x over x minus 1 is just equal to 1. Now look at x approaches infinity for e to the x over x squared. Well, e to the x is an exponential. Exponentials with bases greater than 1 look something like that. So as our x's get huge, our y values will get huge, so this will go towards infinity. And if you go towards infinity and square it, it's still going to be huge, so that's also going to go towards infinity. So we have an indeterminate form. This means we'll do L'Hopital's rule. So we'll reevaluate our limit as x approaches infinity. Derivative of e to the x is e to the x. Derivative of x squared is 2x. Well, e to the x as x goes to infinity is still infinity. If you double infinity, it's still huge, so it's infinity again. So now we have a case where we're going to have to do L'Hopital's rule another time. And that'll often be the case. It might not get us something that we can work with just with one. We might have to do a few things. So we'll do limit as x approaches infinity and take the derivative of each. We'll have e to the x. Derivative of 2x is just 2. And now we'll reevaluate. E to the x, we've said several times, is just infinity. On the bottom, we have 2. If you have an enormous number and divide it by 2, you still have an enormous number. So what that tells us is our original limit as x approaches infinity of e to the x over x squared is infinity. So as the x's get big, the y's will also get big. Example 3, natural log of x. Our graph looks something like this. So as our x's get large, our y's also get large, so that goes towards infinity. Cubed root of x, as you take huge numbers and take the cubed root, they're still going to be huge numbers, so that's going to go towards infinity. So this is an indeterminate form. When we take the derivative here, keep in mind we're going to think of that as x to the 1/3. Okay, we're not thinking of x to the minus 1/3 because we're taking the derivative of that individual thing, not of the whole fraction. So on top, derivative of natural log x will be 1 over x. So we'll have the limit as x approaches infinity of 1 over x. And our derivative of x to the 1/3 will be 1/3 x to the minus 2/3. Now, we don't want to go ahead and plug in right now. We want to try and neaten this up first before we do our direct substitution. And in reality here we have infinity, so we're going to think of it as a huge number. We're not necessarily going to plug something in. So this is really the limit as x approaches infinity of 1 over x. Bring that negative x to the negative 2/3 down, so this is all over 1 over 3x to the 2/3. And off to the side, we can do a little keep change flip. Currently, we have 1 over x divided by 1 over 3x to the 2/3. That's 1 over x times 3x to the 2/3 over 1. You can take a 2/3 x to the 2/3 out of each part. So that's gone, and this will be x to the 1/3. So really, we're just going to have the limit as x approaches infinity. On top, we'll just have a 3, and on bottom, we'll have x to the 1/3. Now we can think as that x gets huge. When you have 3 over a huge number, even when you take the cubed root of it, it's still going to be a huge number. So we'll have 3 over infinity. As the denominator gets huge and the top stays the same, like if you have 3 over 20, 3 over 200, 3 over 2,000, 3 over 20,000, your fraction is going to go towards 0. So what we just determined is our original limit as x approaches infinity of natural log of x over cubed root of x. That limit is just 0. One more example with this type, and this will be the trickiest of the 4 we've seen. We've got a tangent. Let's think about what tangent's graph looks like. It has asymptotes at negative pi over 2 and pi over 2, and then is increasing in that interval. So from both left and right, your limit, you're getting close to 0 there. So when we plug in 0 to tangent, we get back 0. Minus 0 is 0, and 0 cubed is 0. So this definitely falls into the case of an indeterminate form, meaning we can do L'Hopital's rule. The derivative of tan is secant squared. Derivative of x is 1, so we'll have secant squared x minus 1 all over 3x squared. Well, one of our Pythagorean properties. Remember, the one you should always remember, sine squared x plus cos squared x equals 1. We're working with a secant squared on top, meaning that's really a 1 over cos squared. So let's divide everything here by cos squared x. Sine squared divided by cos squared will be tan squared x. Cos squared divided by cos squared is 1, and 1 over cos squared is secant squared x. Notice if we subtract the 1 over, we get tan squared x equals secant squared x minus 1. That means we can replace our numerator with just tan squared x. So this is the limit as x approaches infinity, or sorry, as x approaches 0, of tan squared x over 3x squared. We'll now sub in 0 to do our direct substitution. We saw tan of 0 is just 0. 3 times 0 squared is 0. So we can go ahead and take our derivative of each part individually. Now it's important to note, tan squared x is really saying tan x the whole thing squared. So that's going to be a chain rule on top. The 2 will come out front. We'll have tan x to the first times derivative of the inside. What we saw before, derivative of tan x is a secant squared x. And then we'll be all over 6x. Well, we're going to get a little fancy with this here and neaten this up. The 2 over 6 really reduces to a 1/3, so we're going to leave that out front. We saw in Unit 2 that a rule you can do with limits is you can split it up if you have a product. So we're going to rewrite this as the limit as x approaches 0 of secant squared x times the limit as x approaches 0 of tan x over x. Well, as we carry these down, 1/3 is just 1/3. The limit of secant squared x as x approaches 0. Well, let's look and see what does the graph of secant squared look like. Secant is 1 over cos. Cos will be 0 at pi over 2 and negative pi over 2. So we'll have asymptotes there. Cos is 1 at 0, so that means secant will be 1 over 1, so that'll be 0. And then secant's graph in that section will look like that. So the limit as x approaches 0 secant squared, well, because secant x is just 1, 1 squared is 1. So we have 1/3 times 1. And over on the far right, when we do direct substitution, we get a 0 over 0 case. So we're going to have to do L'Hopital's rule. So this will be equal to times the limit as x approaches 0. Derivative of tangent x we've seen several times as secant squared x all over 1. So if we carry them down again, we've got 1/3 times 1 times Secant squared over 1 is just secant squared. We just saw a second ago as x approaches 0, that is just, in fact, 1. So in the end, we have 1/3 times 1 times 1 to give us 1/3 for the value of our original limit. Remember that original limit was tan x minus x over x cubed as x approaches 0. So these are the most common indeterminate forms. I'd say you see these type probably about 65 to 70% of the time, the 0 over 0 cases or the one of the infinities over another infinity. There are a few other types that can be rewritten in this form. First, let's look at this case. We're approaching pi from the left. Well, sine x, remember the graph of sine x looks something like this, where pi is right here. And the graph of cos x looks something like this, where pi is here. So when we do direct substitution, sine of pi is 0, cos of pi is -1. So we're doing 1 minus a -1. That gives us 2. Notice this is not a 0 over 0 case. This is not L'Hopital's. 0 divided by anything is just 0. So in fact, this limit's 0. This is one where you would not have to use L'Hopital's. So I just caution you, always check and make sure it's an indeterminate form. And again, I'll want to see that it's like a 0 over 0 or an infinity over infinity on any tests, quizzes, problem sets, things like that. Now, just a caution, to always check to see if it's an indeterminate form. And here's why. If you do L'Hopital's rule and it's not needed, you might end up getting an answer. But that answer might not necessarily be correct. Now, the graph of this, x over x minus 4, what it would look like is we would have a vertical asymptote at 4. Because we have the same degree and the coefficients are 1 over 1, we'd have a horizontal asymptote at 1. Well, when you have numbers bigger than 4, you'll have a positive over a positive, so it will look like this. And when you have numbers that are less than 4, you'll have a negative, so therefore will look something like that. For example, like 3 would be 3 over 3 minus 4, so that'd be 3 over -4. So it would be going the negatives. Well, notice the limit at 4 clearly doesn't exist. The left-hand limit is going to negative infinity. The right-hand limit is going to positive infinity. So clearly, this limit should not exist. But let's say you didn't check for indeterminate forms. If you did check, you would notice you'd get 4 over 0. That's not a L'Hopital's case. So if you're not checking and just going ahead and doing L'Hopital's, notice here you would now get the limit as x approaches 4 of 1 over 1. Well, 1 over 1 is just always 1. So you did get a number. Okay, doing L'Hopital's rule will give you an answer, but that doesn't mean it's the right answer. So that's why you have to always check. Make sure you have an indeterminate form before you do L'Hopital's rule. So there's other cases where we could be unsure what is happening with our limit. Next one is indeterminate products. Let's say you had either a 0 times an infinity, or it could also be a 0 times negative infinity. It doesn't matter the sign. This is indeterminate as well. The reason it would be indeterminate is we don't know which thing is happening faster, which is controlling the value. If you're going to 0 more quickly, then the whole thing will go towards 0, because 0 times anything is 0. But if you're going towards infinity much faster than you're going towards 0, then the infinity will control things, and you'll go towards either positive or negative infinity, whichever it is. So because it's kind of ambiguous, we don't know, this would be another indeterminate form. Now, you can only go ahead and carry out L'Hopital's rule, though, if you have a 0 over 0 or an infinity over infinity. So what we'll have to do is try and write it in that form. And here's what we'll do in this case always. Let's forget about the negative for right now, because the negative is not going to change anything. Let's think of this as 0 times infinity over 1. Let's say we undid keep, change, flip. That makes it 0 divided by 1 over infinity. So that means we have 0 over a 1 over infinity. Well, 1 over infinity, when your bottom gets huge and the top stays the same, that just becomes a 0. So that just becomes a 0 over 0 case. So what you can do is just divide one of your functions on the bottom by 1 over that. Here, what if we had done the other one? So what if we thought of this as infinity times 0? Well, let's think of this as infinity times 0 over 1. If you undo keep, change, flip, that's infinity times 1 over 0. Oh, sorry, divided by 1 over 0. So we'll write that as infinity divided by 1 over 0. And now remember, that's not really 0. That's what you're going towards. As you're getting smaller and smaller on the bottom there, 1 over 0 should go towards infinity. So that becomes an infinity over infinity case. So when we're putting these zeros and infinities in, that's not really what the number is. That's just what you're getting closer and closer to. Okay, just so you can see an example of that. If you had the limit as x approaches 0 of, say, x squared, which would be a 0, and let's say, and we'll make it come from the, right, and we might actually end up seeing this example. Let's make it like natural log of x. And actually, I think this might be our first example, so we'll just switch to there. And it's x, just instead of x squared. But we'll look at it this case, since we're going to do it anyway. So when you put in 0 for x at 0, natural log of x, remember, looks something like this. And it's not defined in the 0 or the negatives. That's why we're looking at it just from the right. Well, as x goes to 0, that goes towards negative infinity. So this is an indeterminate product. We need to write one of them in the denominator as a 1 over. So our options are, we can either do x over 1 over natural log of x, or we can do natural log of x over 1 over x. Now, having a log in the denominator might be messy, a 1 over ln of x. So I suggest we choose the second one. We'll stay away from this and do ln of x over 1 over x. So this is really the limit as x approaches 0 from the right of ln of x over 1 over x. And we haven't done anything yet other than just rewrite it in a different form. Because you could multiply by the reciprocal and we're just back to our original. But what this does now is we know if you plug in, or if you go towards 0 from the right of natural log, you get a negative infinity. And in the bottom part, when your bottom of the fraction gets really small, 1 over a tiny number goes towards positive infinity because we're coming from the right. So now we have a L'Hopital's case, an infinity over infinity, so we can carry out L'Hopital's rule. This will become the limit as x approaches 0 from the right. We know natural log of x is 1 over x. Let's go off to the side. 1 over x is like x to the negative 1. That'll be negative 1x to the negative 2, which we can rewrite as negative 1 over x squared. Now, before we plug in, we should try and simplify that. Off to the side, 1 over x divided by negative 1 over x squared is the same as saying 1 over x times negative x squared over 1. So when we bring that together, we'll get negative x squared over x, and you can take one of the x's away and just be left with negative x. So this will be the limit as x approaches 0 from the right of negative x. And now when you do direct substitution, this is pretty easy. It just becomes 0. So if you get a 0 times any type of infinity, put one of your functions in the denominator as 1 over that function. Sometimes you might have to be strategic. If you do that and you get stuck, go back and try doing the other function as the 1 over in the denominator. Our third type of indeterminate form, and the last type we'll look at in this particular video, the other one we'll save till the next video, is when you have an infinity minus an infinity. So if you have some function f of x minus some function g of x, and those each approach infinity, so you have an infinity minus an infinity. Well, the reason that's indeterminate is, again, because we don't know which one goes to infinity faster. If the first one goes to infinity faster, that means the first one will be larger, meaning you'll get back a positive number. If the second one goes to infinity faster, you'll be subtracting a larger number, meaning you'll get back a negative. So which one goes to infinity faster plays a role here. If you get this type of indeterminate form, all you'll do is get a common denominator, bring it all together as one fraction, and then you should have either something that can be evaluated or something you can do L'Hopital's rule with. And let's look at a case of that. We've seen that tangent has asymptotes at negative pi over 2 and pi over 2 and looks something like this. And we also saw that secant had asymptotes at the same spots. And it goes through 0, 1 and looks something like that. And the reason we need these is we want to look at pi over 2 from the left. Well, tangent of pi over 2 from the left goes towards infinity. Secant of pi over 2 from the left also goes towards infinity. So this is an infinity over infinity case. Again, I mentioned we want to get common denominators, bring it all together as one fraction, and then we'll take it from there. So we are going to rewrite this as the limit as x approaches infinity of pi over 2 from the left. And we're going to rewrite secant as 1 over cos x minus tangent we'll write as sine x over cos x. Because now we already have a common denominator, and we can just bring it all together as 1 minus sine x over cos x. Now when we do our direct substitution, pi over 2 is like saying 90. Sine of 90 is 0. Or sorry, sine of 90 is 1. So 1 minus 1 is 0. And cos of 90 is 0. So we have a L'Hopital's case, 0 over 0. Derivative of the top, derivative of 1 is 0. That's gone. Derivative of negative sine would be a negative cos x. Derivative of cos would be negative sine x. So we'll forget about the negatives because they'll cancel out, and we'll just look at cos x over sine x. And that's the limit as x approaches pi over 2 from the left. At pi over 2, cosine we saw was 0. And sine was 1. Well, 0 over 1 is just 0. So our overall limit of pi over 2 from the left, as x approaches that, of secant x minus tan x is just 0. And that's all for today's video. We'll see you next class period.